I cannot. Okay, thank you. Good. Okay. So good morning, class. So today, we are going to finish about the aerosol cloud activation. So nowadays for today's or for this class, so we focus on, say, if you have a single aerosol, right, and then under certain condition, like under the degree of supersaturation, depends on your aerosol size and composition, right? Some aerosol can activate it to form cloud droplet, and some did not, right? So then you can somehow get some idea using the Kohler equation. And then, of course, for the Kohler equation, so you can have modified form, right? So you can just consider the soluble salts, like, for example, sodium chloride, ammonium sulfate, right? But of course, we know in the ambient aerosol, so we have some insoluble materials, and also you can have some dissolved or soluble gas, right? So it can also affect, right, the amount of the soluble materials in your aerosol, and then eventually affect your water vapor pressure, right? And then also, of course, the activation, right, process. And therefore, last time we stopped is a very important equation. Is especially for those who are interested in, say, doing the aerosol cloud activation in your air quality model or some climate model, because eventually we do the parameterization, right? So usually you cannot incorporate, right, very detailed microphysics model, right, or activation equation into your climate model, right, and also your air quality model. So therefore, last time, so we talked about a very important, these days, a very important equation to look at the aerosol water uptake, and also, of course, the aerosol cloud activation is called the kappa, right? So kappa here. So the kappa equation. So basically, the kappa is just to remind you quickly, is somehow to try to study so this is your kappa parameter. So it's a hygroscopicity, or we say it's a hygroscopic hygroscopic parameter, okay, of your species. So what's the meaning? Is that the idea is that you try to look at, so if your compound, right, your aerosol, you contain different species. Okay, so how the different species, okay, depends on their concentration or the amount, and also their types, right? So how you affect the water activity, right? So this is a kappa, how to derive the kappa. So we go through some steps, and then last time we stopped here. So last time, so of course, we start with this equation, right, to look at, say, if you have some we call the hygroscopicity or hygroscopic parameter, right, of certain species. And then if we know the amount or the volume of your solute, okay, and also, and how you will affect, right, the water activity. So then you eventually come up with this we call the traditional or the more the standard Kaplan equation. So this tells you like the water vapor pressure, right, above a droplet, right, with the diameter dp, right. So this S, remember the S is the ratio, right, of the water vapor above this droplet, say compared to a flat surface, right. So this is the S, if this is a dp. So therefore, dp is the diameter of your droplet, okay. So and then this the dd here, right? So it's a dry solute, right? So let's say if you have a dry aerosol, right? And then you have a diameter, say this is called the DD, right? And then you will activate it or absorb some water, right? And then form a wet aerosol. So the DD here means is the diameter of this dry aerosol, right? Before uptaking any water, right? And then if you uptake some water, then you become a wet aerosol. Then you can predict the water vapor pressure, right? So using this equation. And more important is that if you remember this term, right? Before this exponential term. So this is we call the water activity, right? So this is the water activity here. So you can determine or calculate the water activity using this. You assume you know the diameter of your wet aerosol, your initial dry aerosol, right? And then more important is the kappa to calculate this water activity. You introduce this kappa parameter, right? So what is this kappa parameter? Okay, so I think you may. So we're going to give you some more information. So don't worry. So this kappa, right? So this effect. So this kappa, how you calculate this kappa value? Okay, is this is the summation of this. This is the volume fraction. So this is the volume fraction of your species I, and this kappa here, Ki or kappa I here, is the hygroscopicity or hygroscopic parameter of your species I. Okay, so the kappa is just a sum. Say if you know the volume fraction of your species and also the corresponding hygroscopic parameter of your species I. Okay, you sum all these and then you give this so-called kappa value, and then you can use this to determine so how your species, that means your solute, so affect the water activity term here, right? At a different wet diameter. And then if you remember, right, for small water droplet, so you still have this we call the Kelvin term, right? So this is this term just to correct the Kelvin effect, right? Or we call the curvature effect. So you can see, I just want to let you know is that if you look at the kappa equation, so what they try to look at is to see if you have some idea, okay, about the composition of the aerosol. So how you affect your water activity, okay? And then you just leave this Kelvin term, so they don't touch the Kelvin term, the idea, so they just look at this. And then you may ask, so why people are interested in this kappa value, right? Okay, so there's some practical reason. Okay, so I just give you some idea. So why these days, so people are very interested to look at this kappa equation, right? If you run in your model, right, the aerosol cloud activation. So why people are interested using this kappa equation? So we'll come back to some a measurement point of view. So I'll just let you know so why people doing this. So because if you do the measurement or in your model simulation, so what information we can get is, so when we sample the aerosol, so what we can do is we can always easy to get a dry aerosol. So we can also measure the size, that means the diameter, and also we can have some idea about their composition. Right. So for example, in the literature, so you always find people can tell you, say, PM 2.5, okay. And then you will have some major species information, right? For example, you can have some ammonium sulfate. Maybe you can have some ammonium nitrate, right? So you have some idea about the composition, right? say maybe you can have maybe 5 microgram per MPref, maybe you have a 2 microgram per MPref. So you have some idea, right, about the species and also their concentration, okay, and then of course their size. And then of course more complicated. So if you have some more advanced instrument, then you can have your organic mass. So maybe you can also have 5 micrograms per MPref, for example. So now how people can use this information to predict the activation, okay. So now you can see if you know the mass, right? So the aerosol. So if this is the mass, so let's say we just simplify our discussion. So you only have, say, 3 species. So this is your ammonium sulfate, and then this is your ammonium nitrate, and then this is the organic, right? So you know the mass. And also based on this mass concentration, so you can also calculate, right, the volume fraction of your species. So you can also calculate, right? So based on these information, right? So you can also calculate the volume fraction. So because assume you also know the density of your ammonium sulfate, the density of your ammonium nitrate, and also the organics. So usually the typical organics is about 1.2 to 1.5 gram per mole. So then you can determine, right, the volume fraction of your species in a dry aerosol. So this you can obtain in your measurement. And also in the laboratory, for each species, okay, so you can also have their own kappa Ki here. So this is determined so how much you can consider this kappa I is determined. So how much the water will be absorbed by the species. So for most hygroscopic species, so they will have a higher value. So for example, so the ammonium sulfate is more hygroscopic, so they can absorb more water. So you will find that they will have different value or higher value for this kappa I here. So you can determine this for individual species. So now, so what we can do, then you can plug in this information, right? If I do my ambient measurement, so I measure some ambient aerosol, I can measure the diameter, right, of that dry aerosol, dry ambient aerosol. I have some idea about their concentration, or you can say their composition, right? So based on this information, so I can also calculate the volume fraction, and also if I know their hygroscopic parameter, right, for my species. So what I can do, I can just calculate this value, right? So this will give me the kappa, right, for my species or for my aerosol. Then I can just put in to this equation. Then I can calculate, right, or to determine the aerosol cloud activation. So therefore, there's some practical reason is for the field measurement. So we say the field measurement. So the kappa is somehow we can apply the field measurement data into some equation and then to calculate the aerosol cloud activation. Okay, so this is one thing. And also for those, you run the model. So also in your air quality model or your climate model, right? If you have your aerosol scheme, so what will happen is, so you can also simulate, right, a aerosol. Okay. And then you can say based on your model, you can also calculate, right, or determine, say, the composition of the aerosol, right, from your model. For example, you can also say in your model, you can calculate, right, the ammonium sulfate, the ammonium nitrate, or some organic species, right? So you can have all these information, right, in your model simulation. And then assume you also know the hygroscopic parameter of the species, okay? Then you can also use this kappa equation, right, to calculate your aerosol cloud activation in your model simulation. So this is there's some reason. So why nowadays and more people or research group try to say study the aerosol cloud activation using the kappa equation. In particular, is for those, I understand some history is if you do the research, if you just in your model, you don't have any organic, you just have the ammonium sulfate, nitrate, chloride, just the inorganic species. So people may not bother, okay, to using this kappa equation. But I'm sure, like if for those, if in your model, if you have both organics and inorganics, okay, in your model or in your measurement, so I'm pretty sure. So nowadays, more and more people will using this equation, at least to calculate the aerosol cloud activation. So this is more like for the research and also for the field measurement. Okay, if you have some field measurement data and then you want to try to study the aerosol cloud activation process, okay, so then you can also use this kappa equation. Does it make sense? So this is, I think I just want to give you more information and then some reason why people are interested in using this kappa equation for aerosol cloud activation. In particular, for those you are interested to run some air quality model or climate model, so people will using this. And if I understand correctly, is people for those if in your model, if you also want to include the organic, okay, so then you will using this kappa equation. So therefore now, if you have your model, so you can know some aerosol composition. So to calculate this kappa, right? So you also need to have this kappa I, right, for individual species. So just to give you some common value. So let's say we have some values for the species, okay, or some common sort or some important species. For example, we talk about the ammonium sulfate. So so this is just their kappa I species. That means the hygroscopic parameter for a specific species. So this is about 0.61. And then you can have some ammonium nitrate, like I mentioned. So these are some common inorganic salts. So this is about 0.67. And also you can have sodium chloride. So it's a 1.28. So you can determine these in the laboratory, okay, for individual species. But more important is for the organics. So okay, for the organics, broadly speaking, so usually, of course, you can have the kappa value for specific organic compound. For example, we can say there's some alcohol, acid, or ketone, so they will have different species. Different species will have different hygroscopic parameter, right? This is a kappa I. But in the ambient measurement, just for discussion, for information. So usually you will not know the species, okay, for the organics. But more importantly, you can get a bulk, right? I mean the total. So say you know the total amount of the organic compound. It says 5 microgram per m cube. But you will not know the concentration for individual species. Okay. So therefore, most of the time, so when people using this kappa, okay, if you look at the ambient data, so you will have this product, just using the product organics, okay, and then the organics, so they have two classes. So usually they have two classes for you. So one is called the aged, and one is called the fresh. So fresh means your organic just formed or emitted to the atmosphere. Aged means the organic compound have been staying in the air or in the atmosphere for a long time, and then you go through some chemical processing or some process. So, but the general ideas of agreement nowadays is an organic stay in the air for a longer time. So that means they will likely go through some oxidation. They will become more oxygenated. So that means they have more polar functional groups. So therefore, they will have uptake more water. Okay. So therefore, they will have a higher kappa value. But for fresh, so usually they just emit it to the air. So without any processing or chemical reaction, further chemical reaction. So they're less hygroscopic. Okay, so therefore they will have a lower value. Okay. So these are just some typical value or range of the value here. So therefore, if you know the information from your field measurement or in your model, and then if you also know the kappa value, right, for specific species, then you can just using this kappa equation here. Does it make sense? So, but the general idea is if your species is more hygroscopic, okay, so you're going to have a larger kappa value. So if your species are less hygroscopic, that means it's less likely to uptake water, so they have a lower value. So therefore, this is just for your information. Is in particular for those PG students. So in case in your model, some updated version, you will come across with this kappa equation. So any question? So I think, of course, you can have details. You can have your details aerosol microphysics in your model, but these are also another common approach nowadays to study the aerosol cloud activation. In particular, like I mentioned, if you're interested to look at how the organic, okay, affects your aerosol cloud activation, so you will use this kappa equation. So any question from the class? So this will be also some good topic for you to explore in your term project. So in case you're interested, so nowadays what I'm showing here, this one, okay, is more like the standard kappa equation. So nowadays, so they will have a more modified form, okay, to consider different effects. So that will be also a good topic for your project. But in the class, I just show you the standard one because this is well established. Okay, so this will give you some at least some ideas or insight. Any question about the kappa equation? Okay. So now then we'll move on. So of course, nowadays, you know that if you want to have an aerosol cloud activation, right? So we need at least we know you need a supersaturation, right? A certain degree of supersaturation so that you overcome, right, the peak of your polar curve. So you need to above this, we call the critical supersaturation, right? So that you can have the activation can occur. So I'm sure nowadays, we don't go into details, so, but just to remind you, so when we look at this, we call the cloud formation. Of course, now you know that if your ambient RH, okay, say is less than 100%, that means sometimes we call subsaturation, right, or less than 100%. So you know that the aerosol, right? So no aerosol. So will be activated, right? Because you need to overcome the Kelvin effect, right? The curvature effect. So therefore, to have the activation, right? So you need to have this we call the supersaturation. You need to have this supersaturation. And then how we can achieve this, we call the supersaturation, right? So usually they have two processes. I think you have the idea. So one is called the isobaric. cooling. So basically it means that you can have think about it, you have air mass right near the surface. So then you have a cooling, right? So you have some warm environment, and then you go to some cold environment, right? So then you have this we call the cooling of some moisture or moist air, right? Under constant temperature, under constant pressure. So this can happen, right? For example, one typical example is the formation of the fog, right? Near the surface, right? So you have the warm or wet air, right? So from cool place to the warm place, and then the warm place to the cold place, and then you have this cooling, right? At a constant pressure here. And other things you will have these is we call the adiabatic, right? Or adiabatic. Adiabatic cooling, right? So basically that means that if you have an air parcel, right? If you rise, so you know that when your air parcel rise, okay. So what will happen is so the air parcel, say this is a high pressure, this is low pressure at high altitudes. So your air parcel will expand. And then if it's called the adiabatic, right? Expansion means when this air parcel expands, so you assume there's no heat exchange, right? And then in that case, so you have this kind of a cooling. So in this case, you also can create a certain degrees of supersaturation. Okay, so these are the two processes that can create the supersaturation. I'm sure. So you have learned these in some of your course. So I'm not going to the details. But what I want to highlight here is that if you look at the degree, but what I'm interested to remind you is so when you say the degree of supersaturation, okay, so how much, right? So we can go above this 100%. So under the typical condition, okay, in the ambient or in the troposphere, okay, so usually this will be less than 2%, okay. So most of the time, when you talk about the degree of the supersaturation, so you are on the ambient, so you always are talking about less than 2%, okay, of degree of supersaturation. So this is also have some implication, right, for your measurement. So in case later we're going to have some brief discussion is you have a device. So you try to measure the aerosol cloud activation, right? So you need to set some parameter, right, for your measurement. So you will find that most of the time in the literature, in the laboratory, or in the field studies, when you talk about the degree of supersaturation, right, they measure. So they will be measured less than 2% or around 1%, okay? Because this is the typical ambient condition, okay? And also because you know the activation, right? So when you say whether an aerosol will activate it, right, to form a cloud droplet, of course that will now, you know, it will depend on the size and also the composition, right? But also it will depend on your environment, right? The degree of supersaturation, the environmental condition, right? So this is also an important parameter. But these are just I'm sure you can learn this in your classes, so that we can go into details. So, but these are the two major processes that we can achieve the degree of supersaturation in the ambient air. But one thing, when we talk about the aerosol cloud activation, so of course we always talk about the condensation, right, of the water vapor to your aerosol, and then to become a cloud droplet. So then we always talk about some mass transfer, right? Okay. So here I just want to have some discussion about the growth, okay, of an individual cloud droplet. So now if you say if a cloud droplet, so you can have some water, right? Water vapor condense, then it can grow. So I want to have some discussion about this growth of individual cloud drops. Okay, so that means that if a cloud drops, and then you still have some growth, for example, you can have some water vapor, right? And then you can condense to your cloud droplet. Okay, then we talk about some mass transfer here. So when you talk about a cloud droplet, okay, so of course most of the time, so when you talk about the cloud drops, so the size is big. Okay, let's say it's larger than 1 micron. So then most of the times, if you remember, right, when we talk about the dynamics, right, of the aerosol, so if you say it's larger than 1 micron, so under the typical condition, so we always in this we call the continuum regime. So now, if you want to say to study, say the mass transfer to a droplet, right? So that means that you're looking at the mass transfer of the water vapor, right, to the droplet. So you can look at so how the mass, right, of your droplet change with time. So if you look at the mass transfer, right, of a water vapor to your droplet, so this is sorry. So this is a dm/dt, right? So this is tells you so how the mass of the drops, right? This is m is the your drop mass. That means the mass of your droplet change with time, right? So of course this will be can be calculated. So this will be 2 pi times the dp. So dp is your droplet diameter dp, and then this is dv. So dv is your water vapor in this case. So let's say we assume we're looking at the condensation of your water vapor. So this dv is the water vapor diffusivity. So dv means the water vapor diffusivity, right? So dv. Okay. And then of course, V is the rate, right? A kind of the flux, you can say, is you are looking at the concentration, right? The water vapor pressure gradient, right? So this is the concentration of the water vapor, right? Say far from the droplet. So basically means you are talking about some environmental water vapor pressure, right? So that means you have some water vapor pressure, right? Concentration in the surrounding. And then, of course, this water vapor pressure gradient, right? So we drive this diffusion, right? Or the mass transfer. So you're looking at these. This is, of course, this is the water vapor pressure, right? At the surface, right? So this is at the surface. So I just using different symbol. But of course, now, so you can calculate this, right? Using the Coulomb equation. So this is just this is basically you can say this is the flux, right? The mass flux, right? From the surrounding to the surface of your drops, and then So when you condense, okay, then you have some water condensed, right? So then your mass will change. Okay, this is the equation here. But of course, you have shown this, we know this equation. But one thing I just want to highlight here is remember, for example, if you consider it's a condensation. So condensation. So let's say you have some water condensation. So you have some water condensation, right? So we know that if you have some condensation process, so what will happen? So if you have some water, right, condense. So you have a condensation here. So what will happen? So you have a condensation process. So we notice that, so you have some heat to release, right? So you have some heat. Remember, so of course you talk about the mass transfer, but remember, so when you have this condensation, water condensation, so you can have some heat release, right, at the surface of your droplet, right? So when you have this condensation, so therefore you can argue, right? So if this process is significant somehow, that means your water condensation, the process is significant, and then you have a certain amount of heat can be released, right, due to your water condensation. So therefore, if you look at the temperature, right, the droplet temperature at the surface will be higher, right? So that means if this process is vigorous, okay, and then you have a lot of heat being released, okay, at the moment. So therefore, you can argue, right, the temperature here will rise at the surface, right? And then the temperature, okay, of the droplet, at least at the surface, right, will be higher than the ambient temperature. Because I think most of the time, so usually we will assume, okay, we assume, say, the temperature of your droplet, right, is the same, say, the same as the ambient temperature. You can't have an isothermal, right? So the temperature is the same. The temperature of the droplet will be the same as the temperature, right, in the surrounding. So usually we make this assumption. But in some cases, so we need to pay attention in case you have a rapid water condensation process. So, and then we know this heat is being released. Then this assumption, okay, so then you need to check, okay, so whether we still can fix this assumption. That means the temperature of the droplet will be equal to the surrounding, okay, temperature. So we need to check this one. So therefore, usually, so when you look at this droplet growth, so of course you're looking at some mass balance or mass transfer. So, but in this case, we also want to do the energy balance. So therefore, if you want to look at, say, your droplet temperature, right? So if you have this water condensation process, right? So you also want to look at do some energy balance here. So of course, you have water condense to your droplet, and then of course your droplet so can also relieve some heat, right, back to the surrounding. Okay. So of course you can gain some heat, right, through the water condensation. but you can also lose some heat, right, to the surrounding here. So then we can just do the energy balance. If we just consider these two processes. So these are just considered two processes. One, of course, you can see from the right-hand side of this term, right? So this is basically the amount of the water condensed, right? So this is the change in the mass of the drop. And then this is just the latent heat, right? The latent heat of the condensation, okay? So basically the amount of the heat released, right, from the water condensation. And then if you have energy balance, right, so eventually some heat loss, and then you reach an equilibrium. So this will be related to your droplet diameter. And then you have this we call the thermal conductivity, right? So you lose the heat, right, to the surrounding. So let's say we just define a term called so this is called the effective thermal conductivity. Of air, okay, so we have some heat loss, and then how the heat loss, the rate, right? Of course, depends on the temperature difference, right? So this is your T infinity, so just your surrounding temperature, right? And then the TA. So the TA is more specific. It's just the temperature, right, at the surface. Okay. Right, so you have a temperature gradient, right? So then you will hit some heat loss to the surrounding, and then you can just assume a single steady state. And you can have this energy balance here. Okay. So now we just want to have some more information here. So if you look at this mass change, okay. So this is the mass change of your drops, right? Or your drop mass change as a function of time. So we can just can also express these in terms of their diameter. So you can also look at the mass change. You can also refer to how the diameter, right, dp change with time. So doing this. So I think so these are just tells so how the diameter change with times, okay, related to the diameter size. So this will eventually give you the volume, and then this will just give you the density, right, times kind of the volume change, give you the mass change. So basically you can link to this mass change to some change in your particle diameter, right, with the time. So I think this is straightforward. And then what I can do now is I try to, because of the mass, it's difficult to tell, but the size is something we can measure more easily, right? So what I can do, I can just put this term here, right? I can replace the dm/dt with this expression, right? So I can just substitute into here. And then now if I'm interested to look at my TA, right? So that means the temperature, right, at the droplet surface, right? So this is something I'm interested. So therefore, I just what I'm doing right now is I just substitute, right? This term I can put into this term, and then I can rearrange this equation. I just want to say on my left-hand side, I just keep the TA. So because I try to find the temperature, right, at the surface of the drops TA, and then I put all the terms onto my right hand side. Okay. So therefore, if by doing this, so let me change the pen. So by doing this, I try to find an expression to calculate the temperature, right, at the drop the surface TA will be equal to 2T infinity So then I can just rearrange this equation, and then I can find an expression for the TA to be equal to the T infinity. It's just the temperature of the surrounding, and then plus, okay, with this term. So this is the latent heat flux density of the water. This is the effective thermal conductivity, right, of the air. This is your droplet size, dP, and then this is the rate of the diameter change, right, the droplet diameter change. Okay, so this is at least this is called the growth rate, right? So this is more like the growth rate here. Okay. So of course, you can see, right, depends on the growth rate. So your temperature can change, right? So the surface temperature of your droplet can change. But usually it turns out that people find that these terms, so somehow related to the growth rate. Okay, because you have this dP over dt, right? So this is the growth rate of the droplet under the typical condition. Okay, this value, so this term is very small. Okay, so much less than 1. So that means that this value is small under the typical condition, say. Or atmospheric cloud drops. So under the typical tropospheric condition, so most of the time, so this value is small. So therefore, if this value is small, so that means that somehow we can neglect it, right? So when the water condensation, okay, so you would not affect, right, the temperature of your droplets. Consider you have this heat loss, right? So you can reach a steady state quickly. So therefore, most of the time, so it would be safe. So I just want to have this a quick analysis to tell you that so it's still safe to assume the surface temperature of your droplet will be equal to your surrounding. So under the most of the condition, atmospheric condition, so you still can make this assumption here. Okay, even you have this water condensation. Okay, so most of the time, okay, so you still can make this assumption here. This makes sense. So, but I think the idea to showing you this is, of course, most of the time we focus on the mass transfer, right, process. But in some cases, so you also need to consider the energy, right, the energy balance, because sometimes, so you will affect the droplet temperature, right, say at the surface. So this is an important parameter because the temperature can affect many atmospheric processes, for example, the gas particle partitioning, some reactions or things like that. So therefore, this is very important to look at the surface temperature. Okay, so of a droplet TA here. And also there's another reason, so is to measure the droplet temperature, okay, at the surface is very challenging. Okay, so it's very difficult to measure, okay, the surface temperature of a droplet. Okay, so therefore, so most of the time to look at these is you need to do some model simulation or calculation. And then here just to show you that under typical condition, so it's safe to make this assumption. But just for let you know, so if you really want to look at aerosol, remember, for aerosol, so there will be a temperature gradient even within the aerosol. So that means the temperature at the surface will be different from the core. Okay, so like the Earth, so you have the different, there's a thermal gradient. Okay, but it's very challenging to measure these thermal gradients, say within droplet here. So just for your information. So in case that you're interested in looking at the droplet temperature and also some aerosol process that involve the temperature. So this is for information. And of course, in the textbook, so if you really want to calculate, okay, the droplet temperature at the surface TA, so in the textbook, so they show you a very fancy equation. Okay, so in that case, so you consider like the Kelvin effect and also the energy balance, so all the parameters. So you can also use that equation, okay, to calculate the surface temperature or the water droplet changes here. But more important thing is that if you really want to get a more precise or more accurate calculation, say your particle size change, okay, with time, so you should look at both the energy balance and also the mass balance. So we want to consider these two balances here. So any questions so far? So therefore, one thing I just want to highlight here is if you combine this kind of the energy equation together with the mass equation, mass balance equation, so you will come up with these. Oh, I just try to find a pen. So what you try to look at is if you just combine the energy equation together with your mass balance equation, so you will have these. So this equation is you just couple these, you combine this equation, okay, in terms of this change in the particle size as a function of time to your mass balance equation. So you will come up with this equation. So this is just another equation that you combine both the mass transfer and also your energy balance here. Okay. But one thing is I want to highlight here is if you look at how your particle size change with time, okay. So you will find that if you look at this equation, okay, so you will find that actually, if you just put this dp on the other side, I just want to address one point in this growth rate equation is you can see that the growth rate of your equation, okay, so you will find that, so you will just inversely proportional to 1 over dp. So dp, remember, dp is the diameter of your droplet, okay. So if you pay attention to this equation, right, so in case you put this the dp on your right-hand side, and then you also find that this is more or less the constant, some constant here. So you can find that the growth rate, okay, will be inversely proportional, right, to the diameter. So it will be inversely proportional to your drop diameter. That means your dp, right? So this is your dp. So that means that in other words, means your smaller droplet your smaller drops, right, will go faster, right, will grow. Faster than the large drop, right, or the larger one. So what's the meaning is that if you plot the graph, so let's say if this is the diameter or the size of your droplet, and then if you have the time, okay. So in case you're under the similar condition, and then you allow two particles with different size to grow as a function of time, so you will find that your small drops will grow faster, right, than your larger droplet, okay? And then you can see if you given sufficient time, right? So you can find that the smaller droplet, right, can catch up the size, right? Can catch up the size. So at the later stage, right, of the growth, okay, if you're given sufficient time, right? So because you can see here, right, the growth of the particle, right, the growth rate will be inversely proportional to the particle diameter. Okay. So the reason for this, you can think about is using the surface to volume ratio, right? So if you have a smaller particle, right? So in case you look at the small particle, then you have the larger surface to volume ratio, right? So in that case, so of course you have a larger growth rate compared to a larger droplets in that sense. Okay. So but I think the main message here is to go through these 2 points. So you want to maybe keep in your mind is remember, so if you really want to have a more accurate, okay, determination of the surface temperature of your droplet, then remember you need to also consider like the energy balance, right, in your equation. For example, if some water condensation or evaporation, right, of your droplets, okay. And then because of these will eventually also affect your growth rate, okay. So therefore, even you want to determine the growth rate, so I just don't show the fancy equation here, but you also need to consider the energy balance, okay. So if you really want to look at the growth rate more accurately, okay. But more important is another message, important message is you will find that in your equation. So the growth rate will be inversely proportional to the particle size. So that means the smaller droplet will go faster, right, than the larger droplet. So I just show you here, okay. So therefore, this is also give you more implication, okay, for the growth rate of small particle. So how they will change as a function of time, okay. Does it make sense? Any question? So of course, you can see smaller particle will grow faster, right, than the larger. So you can also argue, right? It's called the dilution. So just for some quick discussion. So let's say this is the condensation, right? So then you have the water, right, condense to your droplet. So that means that you can argue, right? Initially, the amount of the solute is constant, but when you have the water condense, right? Then you grow, then you have more water, right? For example, here, then you grow, become bigger, right? But the amount of the solute, right, will remain the same, but the amount of the water increase, right, due to the condensation. So therefore, the concentration, right, of the solute will decrease, right? The concentration of the species will decrease, right? Because you have this water condensation. Okay. So therefore, if you have this water condensation, right? So this is the water condensation. So you know that there will be also we call a dilution effect, right? You have a dilution. So because you start with a smaller droplet, right? And then you have more water condensed, so you have a larger droplet. So then you have a lower concentration, right? So this will be more concentrated, and then there will be less concentrated or more diluted, right? Solution. This is more concentrated. So therefore, there will be a dilution effect. And also because you can see a smaller droplet will go faster, right? So therefore, the dilution effect will be also more significant, right? For your smaller droplet. Okay. If you look at the dilution effect, if you're interested. Because the dilution effect will also affect your solute concentration. And then this will eventually, right? Of course, will affect your water activity. And then eventually will affect the size or the aerosol cloud activation. So this is just for information. But the only thing I just want to highlight is remember, so we also, it's always good to make this assumption, okay? The droplet surface temperature equal to the surrounding, but you can also calculate this using the energy balance together with your mass balance equation. And also smaller droplet size grow faster than the larger droplet because of the surface to volume ratio. Okay. So any questions so far from the class? Okay, if not, then I think it's a good time to take the break. So let's take a 10 minutes break here, and then we'll come back at 12:42. So in case you have any questions, you are welcome to ask during the break, okay? Or you can just type in your question. Okay? Okay, so I think we can just resume the class. So, but before we continue, so do you have any questions so far? Any question about like the Kohler equation, kappa equations, and things we discussed just before the break? Okay, so for the aerosol cloud activation, so we have been covered most of the equation. I think I want to present to you or introduce to you. So now we want to have more like the general discussion or maybe some applications. So what we have been learned, right? So how we can apply, if we try to understand some ambient field measurement data in case you are interested to see how we're going to measure, right? Or to determine, say if you have an ambient aerosol, so whether the ambient aerosol will activate it to form cloud and droplet. Okay, so we're going to have some more general discussion. So based on what we have been learned. Okay, so when we talk about the aerosol cloud activation, of course, from time to time, so these are important terms. So we should have keep in our mind. It's called the CCN. So I think you heard about this, right? So CCN means the cloud condensation nuclei. Cloud condensation nuclei. So the reason it's important, right, to have some idea about this CCN, called cloud condensation nuclei, because you can see, so you have aerosol, right? So you have a number of different aerosol, right? So they have different size, different composition, right? So of course, you know, some of them can activate and form cloud droplet, and some cannot, right? So it depends on their compositions, their size, and also the environmental factors, right? So some will activate and form cloud droplet, and then some will not. So for those aerosol, okay, say you can activate and form cloud droplet, okay? So we call them CCN, okay? So this is what we define. CCN means is the aerosol that can activate it and form the cloud drop. So So under specific condition, so then we call this called the CCN. And like I mentioned, okay, under the typical ambient condition, so the degree of supersaturation so the degree of supersaturation in the environment, okay, I mean the atmosphere, so it's a typical less than 2%, okay, so this is the ideas, okay. So therefore, if you do the reading, okay, so you will find that the CCN, when they tell you the CCN, so they will also give you some number behind, say 1%, and CCN, say 0.5%. So you will have this number behind. So CCN 1% means they measure this activation at 1%, okay, degree of supersaturation. So this is the number of aerosols that can be activated, okay, at 0.5%, okay, degree of supersaturation. So therefore, you can also argue, right? If I give you the same aerosol, okay, so if I measure at different degree of supersaturation, right, the CCN can be different, right? Okay, so that's one question from the student. So let me see. Oh no, 2% means the degree of supersaturation is less than 2%. That means if you measure the average, so it will be less than 102%. Not 2% of the aerosol will be activated. It's the relative humidity, the water vapor pressure, the degree of supersaturation. Does it make sense? Okay, good. Not the number of, not the percentage of aerosol. Good. Great. So any other questions? Yeah, so that is good. So feel free to stop me anytime. So in case some things confuse you, and if you want me to further elaborate some points, or you want to explain in more detail, so let me know. So therefore, so just come back to this point is even I give you the same, okay, aerosol. So for example, this is sodium chloride, for example. So if I measure, okay, the CCN, a different degree of supersaturation, okay, so you will also have different number, right? So because you know, depends on the, if you have the general idea is if you have a higher degree of supersaturation, right, more likely, so you will have more aerosol, right, activated to form cloud droplet, more likely. So therefore, your CCN will also increase, right? So this is one of the, so, but the idea is, if you have different condition, right, degree of supersaturation, your CCN will also change. So therefore, when you do the reading, okay, so people will tell you this CCN is a measure at a different degree of supersaturation. So this is important. So now then, people how to determine this CCN, okay, because this tells you so the number of aerosol, right, that can activate it to form cloud droplet, right, under certain condition, right? For example, 1% degree of supersaturation or 0.5% degree of supersaturation, right? So this is one important parameter. So we want to look at or to determine the CCN is we call the critical diameter, okay, DS. So in case, just to show you some examples. So if you say we have an aerosol population, okay, and then assume so the composition is the same across the size. So we call this a size independent composition. So let's say you just assume you have a pure aerosol, okay, pure sodium chloride. So in that case, so you don't, the composition does not change with the size, right? You just have at given size, it's just the pure sodium chloride, right? So therefore, it assumes you have an aerosol population, and also their composition does not change with size. So this is a important information. So I think for those who have some idea about the ambient aerosol, is if you have different size of particle, you will have different composition. Okay, in the ambient aerosol, this is always the case. So, but here we just say that at different size. So basically, you have the same composition. So how people can determine the CCN in this case? So let me show you in this graph, then you will have better ideas about this equation. So first, we need to know, so what's the DS? So DS is called we call the activation diameter, right? For the, we call the activation diameter or the critical diameter, right? So if you remember, so when we look at the polar curve, right? So this is the degree of your supersaturation, right? So this is your droplet diameter, right? So you have a polar curve like this. And then you can determine, right? This is called the critical diameter. So in this case, let's say called the DS. Okay. So now you can see here is if somehow, if you remember, we mentioned to you about we call this stable and this is unstable, right? So this is a stable region, and this is the unstable region. And then you can determine this critical diameter, or we call the critical supersaturation, right? So, but the idea is for this critical diameter, or we call this activation diameter, means that we can, if you remember when we discussed this polar curve, so you will find that for this given degree of supersaturation, right? If your diameter, okay, is larger than this ds, right? So what will happen is they will just call unstable. So that means they can grow, right, to form the cloud droplet at this different supersaturation. If this your particle size is smaller than this critical diameter, right? Or we say this is now is called the activation diameter. So that means that this aerosol will not grow, right? So will not activate to form cloud droplet. But if you're above this critical diameter, or we call the activation diameter in this case, so therefore this particle, right? So if the size is above this, then you will just activate it under this degree of supersaturation. So therefore, if you look at this graph, this NDP, right? And then this is the change in the BP. So this will give you, say, if this is my number distribution, okay, of my aerosol. So let's say I just follow the, if I go outside, I do the measurement, okay. So this is my NDP, right? NDP, and then this is my DP. So I measure the aerosol at different size, and then I measure the number concentration, right? So this is my NDP. So NDP here means the number distribution, right? So NDP means just the number distribution of my aerosol. So let's say I go outside, I do the measurement. So this is the particle size, okay, and then at a given size, I know the concentration, the number concentration. This is called NDP. So in case if I measure this, And then if I can determine this ds, okay, for the activation diameter, okay. So let's say this is your ds. So this is your ds is somewhere here, okay. And then you assume the composition is size independent, right? So basically, at a given size, you have the same composition. So then you can argue, right? If this is your ds, so now we have the discussion, right? If your aerosol size larger than the ds, okay, this activation diameter, so they will activate, right? At this supersaturation. If your ds, say, if your particle diameter is less than the ds, right? That means on the left-hand side, okay, of this graph, so you will find that these will not activate, right? So they will not activate to form a counter. So therefore, if I'm interested to look at the CCN, right? So that means that we're looking at the aerosol that can be activated, right, to form the cloud droplet. At a given, right, degree of supersaturation S, right? So because of this activation diameter, right, it depends on your critical supersaturation, right? But above these size, right? So these aerosol will be activated. So therefore, this is your CCN, right? So the area here will give you the CCN at this given supersaturation. So therefore, this is the meaning of this equation. So assume that if you know the number distribution, right, of your particle, of your aerosol, and then if you can determine, right, the activation diameter, right, at a given supersaturation, and then you take the integration, right, to the infinity. So that means you give you the area here, right? So then that will give you the number of the aerosol that can be activated and then form the CCN, form the cloud droplet at this supersaturation. Does it make sense? So therefore, it is important for us to determine this, we call the activation diameter, or we call the critical diameter, right? Because if you're knowing this, then you can just, if you know the size distribution of the aerosol, by knowing this activation diameter, then you can determine the CCN in your equation or in your model, right, calculation. But of course, like I mentioned, right, so this implication is we assume we call the size independent composition. But of course, we know that at different size, so you will have different composition. For example, you can have more ammonium sulfate, or you can have less ammonium sulfate, for example. So that means that the idea is that in the ambient aerosol, so if you have different size, at a given size, their composition can be different. Okay. So that means so that's why your usually most of the time, so you'll find that if the composition is size dependent, then aerosol size dependent. So now, of course, the story will become more complicated. You cannot just use this activation diameter and then you do the integration, right, to determine the CCN. But you can do some correction. So now you will just introduce one more term. So assume you also know the aerosol distribution. But now because your composition changed with the size, so you cannot just using this one. And then you just introduce this SF, so FSDP. So this is we call the fraction of aerosol. So then you need to introduce another function. So this function telling us the fraction of the aerosol, okay? And then let me draw another graph. So you can have a very similar distribution, but now you cannot just simplify, define the activation diameter. Okay, so you just say in reality, so you just maybe have only a fraction right here. So this is your CCN, okay, at a different S. So therefore, you need to find a function, okay, this Fs dp to determine or tells your model, right? So this is the fraction, okay, of your aerosol at a given size that will be activated, okay, at this given SS. So therefore, in most of the time, so this will be more complicated. So in cases where composition is size dependent, so now you will be just more difficult to do your modeling in this case. But if you have more simplified system or you have a pure aerosols, then that would be easy. So you just determine the activation diameter. So there's some other more common ways to, or more simplified way to do the parameterization or to estimate the CCN in the model. Is people can say if you have a CCN, okay, at a given degree of supersaturation, so you can relate it to using this equation. Okay. So this C is say is corresponding to CCN you measure at 1% degree of supersaturation. So let's say you do the measurement at 1% of degree of supersaturation, you determine the CCN. Okay. Then at different, of course, you know the CCN will change, right? Depends on your degree of your supersaturation, right? So how you can say this? If you measure 1%, if I say I want to know this is a 0.05% or 1.5%, so what will be the CCN? So then you can use this equation. Assume you measure the CCN more like at a reference state. Now this is called the 1% degree of supersaturation. This is the supersaturation that you are interested. I mean, it will not be 1%, maybe 0.05%, 0.15%. Okay, so this is the S. And then you just take this to exponential of K. You just assign some K value. And then this K value is depends on your measurement. You just do some measurement, and then you do the fitting in your place or in your model. So then you just try to do this correlation, okay, and then just simplify your simulation. So basically, the idea is that you can measure in reality. So you can measure these. I just give you some example. So you can measure the CCN, okay, at different degree of supersaturation, okay, and then you take the CCN at 1% of degree of supersaturation as your reference state, but you also will have the data at the same time, say at different degree of supersaturation, and then you try to fit into this equation, okay, and then you using this, then you can just once you get the K, okay, then you just apply this equation in your model. So this is how people do the parameterization. It's a simplified way to do this, to look at the CCN. Okay. But this is all these we call some empirical. So these are just some empirical parameters. So purely based on the measurement. So purely based on the measurement. So you measure. So that would be some problem. So if this equation is developed, say you try to apply this equation, so but this equation may be developed in Europe, in UK, or in US, or South Africa, or China, and then you try to apply to Hong Kong, then eventually you will see the problem, right? Because you can see all these empirical parameters, right? This is C and also the K, okay? So they're more like the site specific, right? Or system specific. So it depends on the location, right? Or the condition, right? The C and also the K, right? So then if you try to apply the people's result to your place, then you need to be pay attention, right? Because this they not be applied for a case. Because for example, we can argue, right? The aerosol composition, right? Will be very different, right? In their places and your place or your location, right? Of interest. So therefore you need to be careful. Okay. So in case you want to apply these from the literature here, so you need to pay attention. Okay. So one more thing, just want to let you know is, of course, you will have some idea about the ambient aerosol number concentration. And then CCM, remember, CCM is the number of aerosol, right? Say per M cube or number of aerosol per cm cube that can be activated, right, to form cloud droplet under certain condition, right? So the typical condition, say, is a 1% degree of supersaturation, okay? If you look at the CCN, so in some continents, say, for example, in some urban area, so the typical CCN at 1%, remember, the CCN will also depends on the degree of supersaturation. So we are talking about. So let's say it's a 1% degree of supersaturation. Okay. The CCN is typically in the urban environment. Can be 200 to 1,000 per cm cube. So that means that in 1 cm cube, so you will have 200 to 1,000, okay, CCN. Okay, in this case, in the urban environment, in the open ocean, so you will have less aerosol and also you will have less CCN. So maybe around 10 to 100, okay, CCN per cm cube. Okay, remember we talk about per cm cube of air. Okay. So these are just to give you some typical ideas. So you are not talking about in 1 cm cube. Okay, you are not talking about thousands or 10,000s of CCN. So you're talking about thousands or to hundreds. Okay, this is just the ideas. Okay, so that's a question from the student. Oh, okay. So the question is, I think you're going to ask, so whether this activation diameter is the only parameter, right? Yes. So if this is, say, if your composition, like we mentioned in this case, good question. So in this case, if you assume the size, the composition of the particles is independent of the size. So if you can determine this ds, the size is the critical parameter, right? Because this is a good point. Maybe let me so I think we mentioned this before, right? So if you look at the CCN, so basically now we know we have 3 parameters that are important, or 3 main factors. So one is the size, second is the composition, right? And then the third one is the degree of supersaturation. Okay. So therefore, if you in this case, so if you assume the composition does not change with the size, so that means you need to move. This is fixed, right? You don't need to worry about this. And then also you fix the degree of supersaturation. So therefore, in that case, so this is a good thing. If the size is larger than your ds, then you just activate it. Does it make sense? But we need to assume your composition is independent of your particle size. To answer your question. Okay, good. Thank you. So any other question? So that's why somehow we'll be interested to look at this, we call the critical diameter, or we call the activation diameter. So these will give you some ideas for different size. So whether if you just know the size, okay, so then you will see whether this aerosol will be activated or not. So that would be good parameter. But I think this is bring up a good point. Is I think this is a nice summary. In case if you want to look at the CCN of your aerosol, remember, so these are the three main factors. So we want to consider. So first one is the size, right? So because this will give you the Kelvin effect term, the composition. So this is more related to your solids effect, right? Depends on the solid effect, right? Your soluble material, surfactants, or the insoluble materials, right? So this is the composition. And also you can see this is depends on your supersaturation, right? So you can also argue, right? So if you're just using this graph, so we can argue, say if your supersaturation, right, is below your critical supersaturation, so no activation will occur, right? So you need to somehow above this critical supersaturation, right? So then you cannot find it unstable, right? A stable thermodynamic state. So therefore, they just grow, right? Activated, right? So this is that's why when you look at the CCN, it's also important to look at the degree of supersaturation, like the environmental condition, right? Good point. Any question? Okay. So then we'll continue just to look at some cloud processing. I think so. This is a very good point. Have a nice summary. So in case if you study the aerosol cloud activation, so when you think about it as this aerosol cloud activation, okay, so you should think about these three main factors, right? So that will determine your aerosol cloud activation. To what extent, right? So that will determine. These are the three main factors. Okay. So I want to talk a little bit about some cloud processing. Okay. So we talk about the aerosol and cloud. So remember, of course, we focus on a single aerosol, and then you activate and form a cloud droplet. Okay. And then once you have a cloud droplet, then I want to talk about some we call the cloud processing. Cloud processing. So when you talk about the cloud processing, of course, you talk about some cloud droplet. Okay. So these you can imagine, right? So of course, we talk about the growth and things like that. But when you have a water droplet, and then you have some solids, right? So you have some compound inside, and also there will be some oxygen, right? In this cloud droplet. So that will be some we call the chemical processing. So we'll not go into detail, but just want to let you know that's another reason why we are interested to look at the cloud formation or cloud processing, because this is also important for the aerosol. Okay. So you can have this as we call the cloud chemical processing, especially so some clouds you form if you large enough, the cloud can have a precipitation, right? But you can also have some clouds called the non-raining, right? So you have some we call the non-raining cloud. So you can just above the cloud can stay there. Okay. So that means that the idea is that you have this cloud, and then you have the aerosol. So we spend some time talk about the activation, and then you form this cloud drops. And then of course you have some solids right inside. And also you can have some gas dissolved. And remember, so you can also have some oxidant, right? Inside the cloud droplet. Okay, so therefore you can have some chemical reaction can happen in this cloud droplet. So I just want to give you one important process is so why we are interested in this cloud processing is to form the sulfate, aerosol sulfate. So we note if you look at the aerosol composition, so you will see that there's a lot of sulfates. Okay. And then so you may ask us where these sulfates come from, right? So one important process is come from this we call the cloud processing. So the idea is we can have a cloud droplet, right? So you have if you have someone we call the non-raining cloud. So what will happen is that you can always have the air mass coming in and then bring you some gas. So in case you have some SO2 in the gas, and then you can bring to the clouds or cloud layers, so they can dissolve into this cloud droplet, right? And then in this case, so when the SO2 dissolve into the cloud, so I think we showed you before, right? So you can dissociate. You can have form some hydrogen sulfide or sulfide ions. And more important is inside the cloud. So like I mentioned, you can have some oxidant. For example, inside the clouds, you can also have some ozone and also some hydrogen peroxide. So, sorry. So what will happen is, so when you have the SO2 dissolved in the cloud, and then you have this oxidant, so you can have some reaction. You can oxidize this sulfide species, and then eventually give you the sulfate. Okay. So that means you start with some SO2, you dissolve in the cloud, and then you have some oxidation, and then you have this form the sulfate. So what will happen is how you form the aerosol sulfate is, so when this cloud droplet, so you can evaporate, right? So you have a cloud, so eventually some of the cloud, they will leave the cloud base and then will evaporate. Okay. So then the water will go away. From the water drop, the cloud droplet. So this is the drop. Right. So in case you have the water evaporate, so then you will just leave your solute, right? So you have some say non-volatile compound. So you can just argue, right? So you have sodium chloride, right, droplet. And then if you just evaporate, so what will happen? So the water will go away. And then you just give you back the salts, right? So you give you that, if this is sodium chloride, the water, so you have the evaporation, right? Then you just give you back the sodium chloride. So this is also the case, right? You have the cloud processing, initially you have the SO2, you go through this cloud processing, you form the sulfate. The sulfate is the iron, so it's like a salt, right? So after the evaporation, so then you will just remain in the aerosol, and then we give you the sulfate, right? So therefore, this is also an important process for the aerosol formation. Okay, more like the regional or global scale. So we also need to consider this process. Cloud processing can give you some. The idea is the cloud processing, okay, can also give you some aerosol formation or some species, okay. So in this case, it's the sulfate, okay. So this is what we call the in-cloud production of sulfate. This is called the in-cloud process production of the sulfate. So I think this has been incorporated into all your air quality models. So in your model, so for your aerosol scheme model, so you have some cloud processing in models, so you will include this one already, or some other inorganic species. So that would be the cases. But I just want to show you one more thing. This is a small term to the research, but it's also important for the aerosol formation. So here, so now you will see that when you have a cloud droplet, and then you have evaporation, and then of course you can give you the aerosol, right? Give you that aerosol. Okay, so because of some salt, for example, in this case, so they are just stay there, right? So they give you back the aerosol. So therefore, you can see this in-cloud processing or in-cloud formation can form some aerosol species like the sulfate. So this is the inorganic. But I want to also give you an important is this is also important for we call the secondary organic aerosol formation for the cloud processing. So called the SOA. That means that you can also form some organic compound. So that means you will also add some organics, or some aerosol organic. Of course, there are many processes that can form the organic. I want to give you one, I think it's an important process. It's called the Gauxol. Gauxol. So why this cloud process is important for the SOA formation, and why I'm interested to give you one example, it's called this Gauxol. If you look at this structure for this Gauxol, this is C2, right? It's a very small molecule. It just is C2. Yes, there's a question, so let me see. Okay, so that's another question. It's called the volatility basis set mechanism for the SOA formation. So volatility basis set is another different topics. So it's not somehow it's not related to the cloud process like here, right? But you are right. In general, you are right. So the volatility basis set is can use this for SOA formation. But now we are talking about the cloud processing. So how the cloud processing lead to the SOA formation. So, but this will not involve your volatility basis set. Am I answer your question? Yeah. But if we have time, we can talk about the volatility basis set. Okay, so we can talk about this. But now that the idea is I want to show you is that the Gauxol. So the thing is that this is a gas phase species. And also it's a very volatile. So what will happen means that if you have these compound, it's a small molecule, volatile. So you can argue, right? So you know that if they are volatile compound, so they will very likely stay in the gas phase. So they will not go to the aerosol phase, right? So that means that you will expect if you have the Gauxol, okay, so you will not form SOA, right? Are you okay with this? So because it's a small molecule, volatile, stay in the gas phase, so they will not go to the aerosol phase by just the partitioning, right? And also the reason why is I think for those that you do the modeling or the measurement, you know, so we have a lot of Gauxol around, right? So you have a lot of Gauxol, so it can come from the VOC oxidation, you produce a lot of Gauxol. So we have a lot of Gauxol in the gas phase. And then we think that this Gauxol or some small compound will not form aerosol because they are too volatile. But what will happen is, so why this is cloud processing is important. It turns out that the Gauxol can dissolve into this cloud droplet, okay? And then they can dissolve in water. So what will happen is, when they dissolve in water, that means that into some cloud droplet. So if they dissolve in water, so don't worry about the chemistry, but the idea is that these are carbonyl groups, so they can just hydrate it. And then they will give you hydration. So don't worry too much. So I'll just give you some example. You just get the concepts more important. If the Gauxol dissolve into some cloud droplet, so they will just hydrate it. So you have the hydration for this carbonyl group, and then give you this alcohol. So now you can see once they dissolve in cloud droplets. So now you form a polyols, right? So you have 4 hydroxy group. So now you can see that now this is a larger molecule, right? And then you have this many functional group. And more important is, so you have this product, and also if you have the Gauss around, you still have some Gauss around, right? So they can react with this hydrated product, and then form some larger molecule. Just to give you one example. So don't worry the exact formula, but the idea is, so you have some Gauss, you dissolve in water, you form this polyol, right? So you have a number of alcohol groups, and then you still have some Gauss around, right? Then the Gauss can react with this hydrated compound, and then form these C4, right? So it just combine. So you can argue so just combine, and then we say there's a name called the dimer. You say just a dimer. Dimer means 2 molecules, right? Combined, so it's just a 2 unit. So it's just call it some dimer. So what will happen is that you can see after go through this cloud processing, you start with a small molecule, but if you go through this reaction inside the cloud droplet, so you can form these large molecule, right? Larger molecule. Okay. Of course, this molecule can further react and then form a number of products. But the main message, don't worry about the chemistry because it's not the focus for this course. But the main message is you start with a C2, small compound, volatile, likely the gas phase, but they can dissolve in the water, form this hydrated compound, and then you have some reaction and form some larger molecule. So now this is C4, right? So you have C4. You just combine these two, right? So it becomes a C4 compound. And then you have some other reaction. But the idea is that now you start with a small molecule, now it becomes a large molecule. So what will happen is when this cloud droplet evaporates. So of course, if there's a small molecule, even you dissolve these, then you have the evaporation. The small molecule will still go back to the gas phase, right? Or the small organic, right? So they will still go back to the gas phase. But if you can form some larger molecule, so what will happen? Now your larger organics, right? So can stay in the, just like the salts, right? They can remain in the aerosol phase. They are not in the gas phase anymore, right? So therefore, in this case, you can see that when you have this cloud processing, so you can also form some organics, right, into the aerosol. Do you see the point? So therefore, you can see the cloud processing, okay, can be also a pathway to form the SOA. I think in my class, we show you that the SOA can come from the gas phase oxidation, right? So you start with the VOC, you do the oxidation, right? And then you form some product. And then you have this partitioning, right? If you remember. So I show you this. So your SOA is come from your VOC oxidation. So now I give you another example is you can have your gas phase species, right? So originally they're in the gas phase, but you can go through this cloud processing, and then you form some larger molecule. And then after the evaporation, they will still remain in the aerosol phase. So basically now you add the organic mass, right, to your aerosol. That means this is called the SOA. So therefore, the cloud processing is also an important route for SOA formation. Do you see the point? And also important is traditionally, so even you have a C2 also, so even you go through this oxidation, so you will not form aerosol because the product will still be volatile, so they will not form aerosol. But these volatile compound, if you go through the cloud processing, so they can actually give you the aerosol. Okay. So therefore, this is also important for us to consider the cloud processing here. So therefore, cloud processing is also an important route or the SOA. I'm sure for those of you run the model, so people have been considered for the salts like this, like the ammonium nitrate, ammonium sulfate, nitrate, so chloride. So they have been considered in most of the schemes. I'm pretty sure. But for those, if you now become more advanced, or now people will start thinking about the SOA through the cloud processing. So then you start to think about this organic reaction also. But this is just one example. It's called the Gaucho, because then you will add additional source of your SOA, okay, for the cloud processing. Does it make sense? So any question? But the only thing I want to add is now I think from the class you know that so your SOA can come from the observation of your VOC, but you can also come from your cloud processing. So you have two things. So now you see what's the cloud processing here. So the idea is you convert some volatile organic species to some non-volatile species after the aqueous phase reaction. So, but this is not the focus of the course. I don't touch in the detail. So, but in case you are interested, you are welcome to talk to me. But I just want to bring up, given we are talking about some cloud physics, so I talk about some cloud processing here, and also related to the errors. Okay. So, any question from the class? Okay. So I want to use the slide. So from the class, can you still hear from me? So you can still hear, right? So I want to share the slide. Thank you. Just to quickly go through what we have been covered. And also, I just want to highlight one thing is the measurement here. I want to use the slide to show you so how to do the measurement. Okay, do the measurement. So I hope that you can see the slides, right? Okay. Let me just show you. So I have a quick go through is now you see, I think we more focus on the so-called warm clouds, so we don't touch about the ice clouds in this class. But at least for the warm clouds, so you talk about the polar equation and also the kappa, right? So I think this is very important for those who are interested to study the aerosol cloud activation, in particular for those that are doing the modeling. And then we talk about the CCN. So it's important to have the idea about the CCN, right? So basically the CCN again means the fraction of the aerosol, right? That can be activated to form cloud droplet at a given degree of supersaturation. So again, so for the Kohler equation, I think more important is you should have some idea about this Kohler curve. Okay, and then one thing is that now you should have some idea is I hope that so why the water vapor pressure right, can above 100% RH, right, for the water vapor pressure. This is due to the Kelvin terms, right, Kelvin effect or curvature effect. And if you look at the Kohler curve here, so basically you can see this is a nice summary. So the Kohler curve is just a sum of the Kelvin effect and also the Raoult effect, that is the Solow effect. Okay. The Solow effect basically means try to lower the water vapor pressure, but the Kelvin effect is to increase the vapor pressure. But of course, we know when your size increase, so now you're more like a pure water droplet. So you don't see any Solow effect and also the Kelvin effect, right? Because you become a large pure water droplet. So therefore, you become close to 1. But when your droplet is still small, so you still can see the Solow effect and the Kelvin effect. So just to remember, so we talk about the hygroscopicity at some point, right? So what we talk about the hygroscopicity is we talk about the subsaturation point. That means below 100%, right? 100% here. So then you can have this phase change. Say, for example, that deliquescence means you have the solid to liquid. Efflorescence means you have the liquid become solid, right? So it's a phase transition. Okay. And then if you go beyond, okay, 100%, then you are using this that we call the Kohler equation, right? So this is an important point here. I just want to show one thing. I'm not sure. Yes. To understand the polar curve, remember, so you should have the idea about we call the critical supersaturation. Because for different particle size, so you will have a critical supersaturation. So you need to about this point, right? So that your aerosol can activate it to form the cloud droplet. And also for a given critical supersaturation, then you have the corresponding critical diameter, right? So also you can argue, right? So if your size is somehow above this critical diameter, so you can just also can activate it at this critical supersaturation. So this is how we use the activation diameter, right, to determine the CCN. So one more thing is you can see from this graph. I think the most important message is if you see the peak, right, the critical supersaturation. So if we increase the mass fraction of the soluble materials, so of course you increase the solid effects, right? So this will help you to lower the water vapor pressure. So therefore, your critical supersaturation will decrease, right, when we increase the mass fraction of the soluble materials, because you have a more solid effect, right? So therefore, you can see the critical supersaturation will decrease. So, but in other words, it more makes sense. People will tell you is if you have a more soluble materials in your aerosol, you can see that your degree of supersaturation will decrease, right? For example, in this case, if you have a pure ammonium sulfate, right? So the critical supersaturation is about 0.15. But if you have some insoluble materials, right? Or you can only have 0.2, right? Of your sodium ammonium sulfate. You have some insoluble materials, right? So then you can see here, right? So your critical supersaturation is about 0.35. Then you can argue, right? So therefore your aerosol will become less easier to activate, right? If you have less soluble materials. This is the idea. So we should keep it in mind. Oh, and also more important is we call the Kappa equation. Okay, Kappa equation. And hope that now you know that if you have some idea about the volume fraction or the mass fraction of your aerosols, so you can obtain from the measurements. And then you also, if you know the Kappa value for specific compound, then you can calculate this Kappa parameter, right? Then you can just calculate, okay, their activation diameter also. So this is the Kappa equation. So this is very common right now. Only the more important thing is with this point. If you have say insoluble materials or some less hygroscopic materials, and your Kappa value will be smaller. If you have the more soluble materials, so then your Kappa value becomes bigger. So we just talk about the CCN. Okay. Okay. So one thing I want to tell you is how to measure this CCN, right? So to measure the CCN, so we will use this we call the cloud condensation nuclei measurement. So what they try to do, I try to show you this graph step by step, is you can see on your left-hand side, you start with we call the polydispersed aerosol. So because from your aerosol atomizer, so you generate particle with different size. So but we want to look at the size effect, right? Because you know the size will affect the activation. So we do the size selection. So we use this we call the DMA, differential mobility analyzer DMA, to do the size selection. So now you can see you can size select your particle. So that's why we give this called the monodispersed aerosol here. Okay. So now you have your aerosol size selected. Okay. So what they try to do now is you pass through it's called the CCN activation CCN measurement. Is you just to fit in this to some degrees of supersaturation, and then you look at so how many aerosols will be activated, and then you can pick the time using this optical particle size. And then you also can measure the number of the aerosol size you have. This is you can measure this two pathway. One on this DNA tool will give you the number concentration. So that means how many aerosols you fit into your CPC or your CCN measurement instrument. And then this CCN measurement instrument also tells you so how many aerosols being activated, right? So therefore, using this information, so we can determine the fraction of the aerosol that can be activated. So therefore, you will have a graph like this. Is people will say to fix a degree of supersaturation. So you can see here, so you can fix a degree of supersaturation. And then you can change your particle size. So you can see the x-axis here is the particle size you fit into your CCN measurement instrument. And then you can determine so whether the aerosol will be activated or not. So you can see here, the y-axis here is the CCN over the CN. CN is basically the number of aerosols you fit into your CCN measurement signal. And then the CCN means the number of particles activated. 0 here means that no aerosol is activated. 100% means that all your aerosols fit into your CCN measurement instrument. So they just activated and form cloud droplet. So therefore, you can see that you can change the particle size. Okay. And then you can measure the fraction of the aerosol that can be activated and form a cloud droplet. So then you will see a graph like this here. So if you change the size, you start with a very small size. If you remember, when your size is smaller than your critical diameter, you will see no activation. And then once you are above your critical diameter, then all the aerosol can just activate it and form cloud droplet. So you can see there's a sharp change, right? Because the idea is so when your particle size just right below your critical diameter, right? So you will not activate it. But when you are above your critical diameter, right? So you just activate it here. So therefore, you will see a graph like this. So once you're above your critical diameter, then you just activate it here. So therefore, they determine the size called the D50. So they use this 50% activation to determine the critical diameter and a different supersaturation. So this is how people determine the activation diameter of the critical diameter at a different degree of supersaturation in the laboratory. Or you can just fit into your ambient aerosols. Then you can also determine fraction, right, of your aerosol being activated. So you can see when the size is small, okay, so you don't have any activation, right? So this is 0. But when the size becomes larger and larger, so then just the activation, then you become 100%. So you see a graph like this. So just for research perspective, so you can see ideally you should see this as sharp change, right? Because once you pass through the activation diameter, so all your aerosols should be activated. Okay, so this should be a sharp change. But most of the time, if you do the measurement, especially for the ambient aerosol, you see this kind of not a shift. It's more likely you see some change, right? Gradual change here, right? Yeah. This is because this is a more like for pure component. If you have a single component, so you should have a sharp change like this. Okay. Like if you have different species, right? For example, the ambient aerosol, right? So you have a different complex mixture. So usually you will not see a sharp change. Okay. So then you see more like a gradual changes here. So therefore, people determine the 50%, okay, to determine we call the activation diameter. So this is the cases. So this is a more likely you see from a pure component, or you have a simplified component or size independent component composition. Then you will see a sharp like this. But if you have a complex mixture, most of the time, so you will see like this. Just for those information, in case you are interested to look at the measurement of the CCN. And also, there's always some debate. Is of course we mentioned to you that when you talk about the CCN, people talk about the chemical composition, people talk about the size. Okay, but you can say which one would be more important, right? So whether the chemical composition is dominant or the particle size is dominant. because there's a implication. So in case if the composition does not bother or significantly affect your CCN, and then your CCN measurement is only depends on or sensitive to your particle size, then that will be have an implication for your modeling. Okay? Because you can simplify, right? In your simulation, because you don't need to worry too much about their composition. I just need to know the particle size. Then I can determine the CCN. Okay? That means the size effect is the dominant effect. Okay? So therefore, there's some debate sometimes ago is that they find that actually the size is matter more than the chemistry. That means the composition, okay, for cloud formation. But of course, this maybe depends on the location. Okay, so where you do the measurement. Okay, but this is still an open debate. Okay, so just for the information. In particular, for those that you are interested to look at the ambient aerosol, so then that will be some implication for your model simulation or your measurement. So just want to pay some attention. So one last thing is just go back to this is why we are interested to look at using the coupler is because just to give one example is most of the time so we can measure the organic concentration, mass concentration, and also the major inorganic species like the sulfate, ammonium, nitrate, and ammonium, right? So you know their mass, and you also can know their volume fraction, and also if you know their hygroscopicity parameter, right? The kappa I, so then you can calculate the kappa else, and you can calculate the activation using the kappa equation. That's why I mentioned to you is that there's a practical reason people are interested in using the kappa equation, right, for the aerosol cow activation. So one last thing is just a highlight here is so people also interested in cow processing. The reason for this is because it can also give you sulfate, for example, in-cow production of sulfate just mentioned, and also more important, I don't show you here. The lecture notes is also you can form the SOA, the secondary organic aerosol. So that's why you also people start consider the cow processing in your model. Because this has some implication for your aerosol formation. So one last thing I want to highlight is, of course, we mentioned the cow has a net cooling effect, right? Global average. But of course, from time to time, your aerosol, your cow is not just a pure water droplet, so you can have some compound, right, into your cup. If in case, if your cow can have some soot or some light absorbing materials, then you can form this what we call the brown cow. Okay, so now you can see the cow is not just reflect the light back to the space, right? Because in that case, then you have the cooling effect, but this is called the brown cow, right? Then you can have this warming effect, right? Because it can absorb the heat. So in this case, so therefore, there's some interest people talk about the brown cow. Okay? So because in case your cow contains some black carbon or some brown organics, so you can have this called the brown. So that can be some implication when you look at radioactive balance. So this is very much I want to cover for the cow droplet, aerosol cow activation. So any question from the class? Okay. If not, then maybe let's take a second break. So maybe let's take a 6 minutes break, and then we'll come back at 1:55. And then after the break, so we will talk about some kinetics issues. Okay. So let's come back at 1:55. 6 minutes from now. Sila, are you here? Okay, so I get a question, so maybe we can just resume the class. So, but before we continue, so I get a message. Yes, so when we talk about the, so there's a question is, so does the supersaturation we talk about just refer to the environmental supersaturation? Yes, you're right. So when we talk about the supersaturation, we talk about the environmental supersaturation. And then the activation is occur when the environmental supersaturation is larger than that of the aerosol. You are right. To answer your question. Okay, good. Thank you. So again, I'm also interested to give you some more idea about the CCM measurement. Okay. So how we can measure this? I think I explained to you using the slides, but I'm not sure you get the ideas. I just want to give you some quick ideas of how we can measure the CCN. Okay, for example, you can have some aerosol, can be ambient aerosol or laboratory generated aerosol, and then you can fit into some CCN measurement device. Sometimes, so how then the question is how we are going to create this we call the supersaturation, right? To activate the aerosol, right? So for example, it can be ambient aerosol, or it can be laboratory generated aerosol. So you can see from this graph is to create the supersaturation. So what we try to do is, so of course you need to provide some water, so you can have some porous materials, or we call wick. So this is saturated with the water, and then you have a warm temperature, and then you saturate with water. So what will happen then? This is a warm environment, then you saturate with the water vapor, right? Here. But you know that this will not create we call the supersaturation, right? So then what will happen is you have this kind of a warm environment, and then once you saturate with the water vapor pressure, so you can see you pass through you go to a colder, right, environment or cold environment. You lower the temperature. So now you can see that you have a rapid, right, temperature change, and then you can see that in this case, so then you can create supersaturation, right? Just like the isobaric cooling, right? So we mentioned before, right? So therefore, in this case, so now you can create we call the supersaturated water vapor condition, okay? And then in this case, and then your aerosol here, then you can just activate it, right? So your aerosol is activated. So of course, some aerosol is activated. And then they will have a detector behind, okay? Because you can see if your aerosol is small enough, okay? If your aerosol is not activated, so you will not be detected by this laser, okay? But if your aerosol is activated and form a large droplet, then they can tell you that, oh, you form a cloud droplet, right? So then you can count, right? This one, okay? So this is how the instrument, okay, to create the supersaturated water vapor pressure condition using this kind of temperature gradient, okay, in this case. I just still want to go back to this graph. So because I remember, so we need to know the size of the aerosol, right, to form the activation. So therefore, most of the time for the ambient aerosol, right, so you can see you can have the distribution like this, or you can have multiple peaks, right? So therefore, one thing is we need to do the size selection. So therefore, the first thing is you have this called the DMA, differential mobility analyzer, right? To help you to do the size selection. Okay, so you can size select the particle you want. Okay, so now you can, that's why this is called the polydisperse, this is called the monodisperse. So then you just basically select the size that you want. For example, this is maybe 15 nanometer, say the mole diameter, so in this case. And then now you go, then you do the size select. Okay. So what they will try to do now, your aerosol will split into two parts. So one here will go to another called the DMA plus a CPC particle counter. So basically, the idea is to look at, so what's the number concentration, right? So after you do the size select, so you want to know the concentration, right? So this will give you the aerosol concentration. Say maybe you can say this is maybe 1,000 ccm, because 1,000 of your particle, right, have 1 cm cube. So you have a 1,000 in this case. Okay. So now the same aerosol, right? So that means that this is a 1,000, right, per cm cube. Aerosol will fit to your CCN, and then you will fix a degree of supersaturation, right? Say, for example, you can say you measure this at 1% degree of supersaturation. So the aerosol will fit in, and then remember, right, like I mentioned, so you can have a 1,000 go in, but in some cases, some will not activate it, some will activate it, right? And of course, in certain cases, so they're all just activated. So then this will give you, if they activate it, then they will count, right? They can detect. If they're not activated, they will not detect, right? So therefore, these instruments will give you the CCN, right? Because they only look at so the aerosol that can activate it to form cloud droplet. So therefore, you have this number. So therefore, you can see here. So if you produce a graph, is that you can do the size selection. You can change different size, and then you measure the number concentration, and also at the same time you measure the CCM. Then you can plot this graph. Right? You can just, for example, you measure 50, then the next one you measure 60, and then you go to maybe 100, 200, and then 500. Then you can have a point here, right? So you know different concentration and then the fraction that can be activated, right, from this. So then you can plot this graph, right? And then you can start with small particle size. You may not see any activation, right? And then you start seeing some activation, and then you produce this graph. And then usually you set this called the 50, right? So that means the 50% is being activated. So they determine this critical, or we call the activation diameter, right? Does it make sense? So this is how people do the laboratory measurements and also the ambient aerosol measurement. So you can fit in the ambient aerosols. You can also generate, say, pure sodium chloride, ammonium sulfate. So you can fit in all these, and then you can get this information. And then you can determine the activation diameters at a given supersaturation. Then you can change your supersaturation, right? So you can say you can change from 0.2%, 0.5, or 1%, right? So usually we will not go above 2%, okay, most of the time. So any questions so far? I just want to give you, I think this is important somehow for those if you're interested to do the measurement. And to learn about the CCM measurement. So any questions so far? So how you can create a supersaturated water vapor pressure condition using this called the thermal gradient. Okay, so they can have a different device. Okay, so I just show you the principle. Okay, of course they can have different configuration. So you can have warm, so you can hot, cold, hot, cold, hot, cold, and then you can also have different configuration to create this supersaturation condition. So, but this is just some the basic working principle. So any questions so far? Okay, then we've finished the aerosol cloud activation. So now we move on to another topic. So we're going to talk about some mass transport. Say to or from a aerosol or particle. But what I want to more focus in this part is we want to look at is the kinetics. Kinetics issue. So of course, I think for some of you, if you do the model simulation, so most of the time we assume you can reach a steady state, right, or equilibrium state. So in your simulation, right, so that will actually help you to simplify your simulation or cases. But I think from time to time, or at least now, so when we talk about the aerosol. So even you talk about the aerosol, for example, if you're interested to look at these, we call the gas particle partitioning, right? So for example, you have a species, right? So you have this gas particle partitioning. I think in my classes in atmospheric chemistry, right? So I tell you that this gas particle partitioning, so you can say you can achieve a equilibrium state. And also it's a reversible, right? At a given time scale that we are interested. But I think for those now you know that for the aerosol, okay. So these may not be a good assumption anymore, okay. So that means the idea is that for different time scales, okay, even in your model simulation in the atmosphere, so you will find that actually this gas particle partitioning, so usually that you cannot reach the equilibrium state, okay. it takes a long time. The idea is it takes a long time to reach the equilibrium state. So therefore, there's an implication is that you cannot somehow do this studies assuming equilibrium, okay, or reversible. So therefore, you need to take care about we call the kinetic. And then you may ask, so why we not achieve this gas particle partitioning, right, or gas aerosol partitioning easily, right? So because nowadays, of course, if you have a droplet, so you can reach equilibrium very quickly. For example, the water drop or cloud drops. So the water equilibrium is fast, okay? The diffusion is fast, all these things fast. But the thing is that now for the aerosol is different. So we know the aerosol can be a very concentrated droplet, right? And also you can have different species. The one problem for the aerosol is now if you have some idea is that so we have this viscosity issue. So because some aerosol, because they have a concentrated solution, so also depends on the composition of the species. So what will happen is your aerosol can be a very viscous. Okay, you are not talking about some water droplet or solution, dilute solution. You're talking about some very viscous droplet, maybe some semi-solid or sometimes solid, or sometimes we call some very viscous. Maybe sometimes they usually now some literature say you can more like a ketchup, okay, or honeycomb, okay. So therefore, because it's very viscous, okay, so this will affect the transport, right? The mass transport will be affected, okay. So if you imagine, right, if your aerosol is very, very viscous, okay, like a ketchup or honeycomb, so the diffusion of your species is very slow, right? So therefore, your transport is very slow. So therefore, you will take a long time, right, to reach the equilibrium state, right? Do you see my argument? If your aerosol is very viscous, okay, it's not a solution, it's not a droplet, it's very viscous. Then you have this we call the mass transport issue, okay. So that will have a lot of implication, in particular, for the SOA formation, because nowadays most of the model you run in your model, for those who run the model, you assume you can reach an equilibrium, okay, and then you have this reversible reaction. But this is not always the case, okay. If you really want to get this right, so I think somehow you need to also consider the kinetic issue. So that's why now come back to this kinetic issue. Okay, so of course this kinetic issue is also depends on number of factors. Okay, so even you can say, so if this is a viscous aerosol, okay, but under certain conditions you still don't have this kinetic issue. But under certain conditions you will have this the issue. So because overall you need to compare with different process, right? The time scale. More important is if you want to look at whether you have this kinetic issue or we say the mass transport issue, right? So you always want to compare or to look at this we call the time scale issue, or we call the characteristic time scale, right? So I think you talk about like say the mixing time scale, the reaction time scales, or the transport time scale, right? So you want to compare or look into this time scale for different process, and then you can define. The idea is that you will define under what condition. So you will have this mass transport problem, and under what condition you will not have a mass transport issue. Okay, so because of so whether you have this mass transport, so idea is for this mass transport issue, or sometimes we call mass transport limitation. So that will also depends on what kind of process we are talking about, and also under what condition. So under certain conditions, you will not have the problem. But under certain conditions, you will have the issue. Okay. So that's why we want to spend some time to look at the time scale for different process, and also to tell you more about the importance of the kinetics, because most of the time for aerosol science or aerosol study, or even your model simulation. So because most of the time people still assume you can reach the equilibrium, okay, state. So, but at least for state of art studies, so you will know that this is not always the case. So you can also have this kinetic issue. And one potential reason why you will have this kinetic issue for aerosol is because of the viscosity of the aerosol. Of course, there's some other parameters, so we'll consider, but one information is the aerosol can be very viscous, okay? So that will affect some of your mass transport, okay, issue. So that we need to take into account, okay, when you do your model simulation or when you do your studies, okay. So I think because of the time, so I think I'm going to stop here for today. So the next lecture, so we're going to talk about the mass transport issue, okay. Any questions so far from the class? And also, I think because of the time, I think you should also start thinking about your term project, okay. And also, if you have any question about your term project, you're always welcome to talk to me, okay. So if you have some ideas about your topics, or you're still thinking about your topics, so you're welcome to talk to me, okay. So I will going to send out the details next week, okay, or before the study break, okay. But if you have any question about your individual projects or term projects or literature reviews, so you're welcome to talk to me. I think it's a good time for you to start thinking about your project titles or contents, okay. So any question from the class? Okay, if not, then I will see you next week, okay. So bye-bye.